Okay, so first of all, I want to say this is such a wonderful workshop, and it's been so enjoyable so far, especially Jonathan Frankel's incredibly honest spotlight a little while ago. I also have been through that roller coaster for many years, and the first 8 NeurIPSs that I went to were felt like I was hustling and under a spotlight. Now I'm a little more relaxed, and I guess it feels a little bit saccharine to say, oh, here's kind of a victory lap. Here's one where people actually liked the paper more than I was expecting. That never happens. But this is a little bit more about riding the tiger, and when we did get a bit of attention, how that kind of made some stuff happen that I didn't expect was going to happen. So that I wasn't ready for. So the origins of this paper were actually, it was one of 8 submissions that year, of which all but 2 got rejected. We originally had this long and unpalatable title, Training Infinitesimally Layered Neural Networks by Backpropagating Through Black Box ODE Solvers, which really tells you what we were doing, but it doesn't sound sexy and it's not memorable. And we actually had a long series of discussions about wrestling, well, should we? There's this one really short, awesome title, and it's kind of obnoxious because I kind of really dislike it when people just take cool sounding words and put them together, maybe even tensor is overused. But eventually we did choose the sexy title, and it definitely paid off in hype. And then we pulled in, me, Jesse, Ricky, and Yulia pulled an all-nighter on that submission deadline, and I hope it's my last. I'm going to quickly go through some of the claims that I made, or maybe things that were a little bit misleading, that when we package this into a nice story for talks, I'm not going to say these are false, but that there was a simpler message that we pushed than what is the truth here. So one is the motivation, which we said was due to, actually, Yulia had a data set of gene assays that were irregularly sampled through time. And we were going to bin them like everyone else does, and we could have done something a little bit more sophisticated. And I thought, oh, I know. There's this, we could do the gold-plated version, which is to actually do this in continuous time. And I know that you can because I looked into this a long time ago when we were writing AutoGrad. And the original motivation for all this stuff was to impress my co-authors of AutoGrad, the Python autodiff package. We would sort of after we wrote, Dougal wrote most of the core logic, we had to go through and write the gradients of all these different functions, like sort, or take the eigenvalues, and each one was a fun little puzzle, and we kind of would sort of tease each other with these interesting puzzles, and this one I thought would be impressive. I actually think that if I wasn't in academia, I would hardly publish, because if I could just, impress the 3 or 4 people around me that I most respected, I would consider myself done, and so that's one nice thing about this job, is that you're forced to publish even though you don't want to. Okay, so when this application came up, if I hadn't already had looked into it before, we wouldn't have done the real nice version. And I remember saying to Jesse, oh yeah, let's just do it. It'll be 5 lines. It'll be running the SD or the ODE backwards or something. Okay, so this is the real doozy. This is one that is actually bullshit, and it's actually a wrong claim in our paper, or rather an unsupported claim. So we had our 5 reasons why neural ODEs were cool, and one of them was parameter efficiency, saying that we could make the layers in adjacent depths automatically tie by having this hypernetwork. And you can do that, but you can also do that with a standard ResNet. And we had an experiment comparing against a MLP with more parameters, but there was a little bit of a breakdown in communication that's entirely my fault. And I didn't realize that Ricky hadn't tried to see how few parameters he could use for the baseline. So this is 100% wrong, bad, and we've actually, this talk has been the kick in the ass I needed to finally update the archive version, so we just submitted that a minute ago. So this might be true. Yeah, I know, a year ago. It's still going to be 2019. Anyway, so this might be true, but we didn't demonstrate it in the paper, and that was just a fuck up, and yeah, that's what this whole workshop's supposed to be about. Okay. This is one that came up every time I tried to talk to differential equations people, the numerics community, who from my point of view, I said, this whole thing is an homage to you guys. You've done all this amazing work over 50 years, and now we have these really powerful ODE solvers that can adaptively choose step sizes and evaluate in sophisticated ways, and that lets us use these as black boxes in our deep learning models. In particular, we had this nice plot showing that as we adjust the error, the tolerance that we send to the solver, that's the error that the solver gives us. So it always matches the error budget that we asked for. And whenever I went to talk to ODE people about this, they said, yeah, I'm saying, this is great. This is a really cool set of tools. And they're saying, no, the whole point of our field is that you can't just always expect it to work. And there's going to be all sorts of weird ODEs where you can get yourself into trouble and things can silently fail. And at first I thought, well, these guys are being prickly. And then I realized, well, like think about when you hear some like deep learning consultant, they're like, oh yeah, we'll just feed the data to the AI and then it'll learn automatically and like find all the structure. And we're like, no, the whole point of our field is that it's hard and that doesn't always work. So that was a little bit of perspective that I gained from talking to the people whose tools that we were, importing. So one other one, sort of bullshit that I was saying is that these are a drop-in replacement for ResNets. And this is like, I'm just copying a slide from the slide deck that I used to talk about this. And I say any time that you have a ResNet, you can replace it with an ODE net. And empirically it works the same and can use the same training algorithms. And then there was actually some really nice theoretical work. Like a couple people, when we first released this, said something like, oh, but you're only learning a diffeomorphism. Isn't there some funniness that there might be things you can't learn? And we said, yes, maybe, but it's not, important. But actually, there was this really great and satisfying, to me, work, follow-up work, augmented neural ODEs by Emilien Duvenaud, Arnaud Disset, and Yu Tay, that pointed out that actually there are cases where learning a diffeomorphism is a problem. And for instance, you can't learn simple one-dimensional functions like f of x equals negative x because you can't cross the streams in an ODE. So you need to add extra auxiliary dimensions. And actually, this bit us in one of our toy experiments in one of the follow-up works that we were doing. So there was a lot of, I just started learning about ODEs at the beginning of this project, 2 years ago. And a lot of people came in and said, oh, but isn't there this technical thing where sometimes it's a problem? And I was maybe a little defensive sometimes. And now I'm realizing that every time someone said that, later on, someone else came back and found a situation where it actually did matter, and I was too quick to brush it off as a technicality. Oh yeah, and this is the amazing plot they made of how learning in more dimensions is easier, has simpler dynamics when you don't have to go around someone, you can just go over them. Okay. So I'm afraid I don't have that much bullshit from others because, I only really want to shit on my own work here. I don't want to be too hard on other people. And I will say, so Karen Howe was the reporter, one of the reporters that I met with at NeurIPS last year. And she was incredibly quick on the uptake, very dedicated. And we actually had a series of meetings for, where she learned what we were doing and wanted to make sure she got everything right. However, I was really shocked when the first version of the article said that I had invented this thing called ordinary differential equations and that we were using an ODE solvers. And I was horrified because I thought there's going to be some people who think that I'm actually claiming that. And I really don't want people to think that. And it was really funny because there's actually still a line in the article about how this is called neural ordinary differential equations. They still need to work on their branding. Because I think she thought that the word ordinary was a really lame word to use in your new method. And but we worked all that out for the most part. But there was a serious disagreement, which was that I was saying, well, you wrote the whole article as if I single-handedly did this whole thing, and that's not what happened, and that's not accurate, and it's really important to me that you credit my co-authors, especially because they're students. And so her compromise was, I will say David Duvenaud and collaborators did this, but she flatly refused to add their names, saying it doesn't serve the reader. And I think she's right? I think it makes a better article, it's more engaging, and it's not of use to most of the people who read this, who all the co-authors were and what they did. But it's my responsibility to make sure that this happens. So that was kind of eye-opening to me to realize that the interests of me and the press overlap, but they're not the same. And there's nothing sinister about that, but it's something that you have to keep in mind. So the other thing that happened, of course, is as soon as you get a lot of attention, you step on toes. And obviously, this is an old field, and it's easy to get the impression that we were claiming that we had figured out how to prop through ODE solutions when we didn't. And I think the original version of the paper wasn't 100% clear on this point, and later we updated to say no, the only thing we're doing is bringing this to PyTorch basically, or modern autodiff languages. And I think these guys in the let's say numerics community were rightly annoyed that it sounded we just reinvented something and we're hey guys, did you know there exists this method? I mean, in the paper we're citing left and right, but we could have been more clear about that. And in particular, there's this package. Well, there's a lot of related work, the ideas of neural networks as ODEs and ODEs as neural networks was already in the air, starting especially from Eldad Haber and some people at UBC. And there was actually one piece of software, Cassidy, that implemented all the tricks to make this efficient and scalable. But that was like from 2013 or something. And this guy, that's Joel Anderson, and he's saying, read my thesis, it's all there. And like, he's right. So it's unavoidable to step on toes. And we were already trying to be careful about this, but I think the higher the attention, the more careful you have to be about this, obviously. So then what was fun is like, it was incredibly gratifying to watch everyone build on our work, right? Like that's the coolest thing ever. It was like such an awesome feeling. And that, so someone made this meme because in particular, there's one sort of, I wouldn't say like obvious extension because the technical details are really tough, but just by combining buzzwords, there's like stochastic differential equations would be a cool thing to do. And I think so too. And we've been working on this for a while. We still haven't published our version. And of course, we were like annoyed when these guys choose the same title that we were going to use. But it's not like, we don't own the title. It's anyone can write whatever title they want. So I will say, it was the most relaxing paper in my career to write was Fjord, which was the follow-up to neural ODEs where we just applied it to density estimation. And we knew, because we had a little bit of a lead, that no one else was doing this. And it was the one time when we could actually take our time and do it correctly and not have to sweat every night about, are we going to get scooped? And that's it, because now, these ideas are out there. Lots of people know a lot more about differential equations than I or anyone in my group does. So we're like part of the fray. And then I guess also I'll say like there was some papers from people just playing around with methods that used these in a context where they didn't I think make sense technically. And it's a funny situation. Like I'm not obviously going to call these people out, but like to say, oh yeah, neural ODEs are great. Actually, no, they won't help you there. And it feels bad when some people are like, oh great, I want to talk to the original guy, and I'm just like, yeah, you shouldn't use it. No, just use a ResNet. No, it's fine. So. Okay, so the last part of this talk is just going to be like an outlook, and basically asking the question, well, the original paper didn't have any, state-of-the-art results. It was just, here's a bunch of proof of concepts. We've had some follow-ups, but it's not clear what part of these ideas are going to stand the test of time and when we really need to use these methods. So there was three main things we said that you could do with these in the original paper. So one is as a replacement for ResNets, just for normal deep learning or supervised learning, replace your fixed number of layers with a neural ODE. And this would have adaptive computation and low memory cost. And the second one is time series models where we have irregularly sampled time. And the last one is invertible normalizing flows. So there was this awesome paper that is actually just a spotlight at this NeurIPS, which is deep equilibrium models by Zico Coulter and his students, that says, hey, we can implicitly define a deep network as just a fixed point of some neural network layer. And this has its efficient memory training, and it has adaptive computation where the number of layers isn't fixed in advance. So I kind of think this is really cool that they sort of refactored the ideas a little bit of neural ODEs and say, well, the important part isn't that it's an ODE. The important part is that we're implicitly defining the answer. Then we can approximate it, which is really satisfying intellectually, but it's kind of a bummer when I'm like, oh, okay, well, yes, actually that thing might make more sense. And it kind of felt like it stole my thunder. So, I mean, neither of these are really practical yet, and so they're both waiting for this a story about how can we regularize these to be fast to solve. How can we find dynamics that can be solved in a few number of iterations by the solver. Okay, so yeah, so the second setting is time series, and we originally said let's use this latent ODE model where there's a vector valued hidden state that evolves according to the laws of physics or human physiology or whatever, and we have noisy observations. And I was saying this is really great for irregularly sampled time series. However, it has a really weird property that all the randomness, all the uncertainty comes in the initial state, and then everything else is deterministic after that. So there's no room for all the little weird interactions that you didn't get to observe. So in particular, if we're modeling someone's physiology with this setting, we're kind of saying if they get hit by a car when they're 20, that has to somehow be foretold by the model in their initial state. And we have to cram more and more information about their life in this initial state. It doesn't quite make sense. So this is the only part of the talk that's I'm actually optimistic about, which is that we then need something like stochastic differential equations, and this is what we're working on. And we just barely got it working in low dimensions a month ago, but that's not ready for prime time yet. Okay, so then the third place where we said, okay, this is a real win, is in these continuous normalizing flows. And here's a visualization made by Jesse that says, if we take a Gaussian distribution and put it through a ODE, like pointwise, and keep track of the change of density, we end up with some parametric non-Gaussian density that we can fit to data. And the cool thing is we don't have to partition the dimensions like in real MVP or GLOW. We can just use whatever neural network architecture we want. So then we thought this is a big win. We wrote another paper about it. And then actually Jorn Jacobsen and Jens Berman came to Vector and they started saying, hey, I wonder if we can have some sort of like discrete time version of these flows. Then we could use standard neural network architectures and no ODE solvers. And they actually did work out the math to do this. So now we can say, oh, we had this cool method Fjord, which was awesome because it had an ODE solver in it. And then now we can say, actually, we have this other cool method, residual flows, which is awesome because it doesn't have an ODE solver in it. So again, like maybe these ideas were inspired by the ODE formulation, but now it's sort of vestigial, and it's not clear that that line of work is like a slam dunk that we should be using ODEs at all. There is one awesome bit of work that I totally love is this paper called Point Flow, where they say, oh, what if I want to learn some sort of like non-intersecting manifold or surface? If I just use like a neural network, then it might like intersect itself or have some weird like edges. It won't be a nice like I don't know what the word is, like solid shape. So that's one instance where we actually need to learn diffeomorphisms. So maybe differential equations make sense. Great. So it's only been a year, right? So maybe it's a little bit like funny to say retrospective. All I'll say is that I think maybe one of the main reasons that this paper took off is just that it had a nice figure one that sort of got you a flavor of the main idea. And I have other papers that I feel like are equally exciting, but there's no good way to visualize them, and so it's sort of hard to like explain them in one retweetable image. The other thing I wish I had learned was to just, I think I was not that defensive, but I was a little defensive, and I wish I hadn't been defensive at all, especially when people were making these what I thought were technical nitpicks throughout as we released the paper, because they actually always did have a point. The last thing I'll say is that the only reason that all of this worked is because we, back in my postdoc, we were working on AutoGrad. We learned how automatic differentiation works. I feel like just understanding the guts of that has led to like 3 or 4 papers where it's just like, oh, people still don't realize that vector Jacobian products are cheap. I mean, I think people kind of do now, but having tools that are good enough that you don't have to think about, can I really take the gradient of that thing with respect to that thing, will free your mind. So, as I said, it's my responsibility. I want to say that the bulk of this work was done by my co-authors, Ricky Chen, Yulia Rubanova, Jesse Betancourt, and Emil Grathwohl. Thank you very much.
Thanks, David. We have time for 2 questions.
All right, so you went through this phase where you had no differential equations or ordinary differential, and then you switched into that, and that was really cool, and then you switched out of it, and that's even cooler. You didn't end up back where you started, right? So what did you learn by going through this path that gave you new insights to solve problems?
Right. So it's not the end of the story, and I'm not saying let's abandon these. I guess I'm just saying I want to be careful not to overhype it and say this is the future. I want to say these point to the use of like a bunch of tools that we can use from these related fields. Like in the instance of deep equilibrium models, it sort of says maybe defining things implicitly is a powerful way to do things. I'm obviously not the first person to say that. Yeah, and then I guess just to me the thing that I hope to repeat someday is to say wherever there's a 50-year-old field's body of work that we're somehow not taking advantage of, it's at least worth a thought of like how can we import that knowledge.
Hi, thanks for the great talk. So I have one small question. When I talk to the BDE people, so they mentioned that when they solve the BDE, they usually do digitalization first and then do optimization. But in the Neuro ODE, actually we do optimization first and then digitize into a deep net. So how can you reconcile those two? That mismatch between Neuro ODE and the BD solver?
Right. So the question is, well, the other thing we could have done besides this adjoint sensitivities method, so what we do is we run a new system backwards in time, don't store any of the intermediate trajectory. That's different than the standard neural network where we store all the intermediate layers. And when we store all the intermediate quantities, we're guaranteed to get the exact gradient. But if we reconstruct things, there's a chance that numerical error will make the forward and reverse trajectories diverge. And this is a real issue. And all I'll say is that we wanted to, the adjoint sensitivities method has these nice scaling properties, but if it's failing for some reason, we can just tune down the tolerance of our solvers and see if that fixes it. If it doesn't, we can do some sort of checkpointing. I'm not saying that we shouldn't be flexible in how we do these computations. Yeah.
Thanks again, David.
Cool.